when I take the derivative of an antiderivative, such the derivative of a constant is 0, C can really be anything. So we describe the entire set or the entire family of antiderivatives using plus C. Today's focus is what are differential equations. How we are going to solve differential equations. That differential or differentiation word means what? Differential refers to what? Say it. Derivative. A differential equation is just an equation in terms of the derivative, right?
Yeah.
So f prime of x equal to 1/2 x minus 1, for example, that's a differential equation because aren't you given the derivative?
Yeah.
So if I'm given the derivative and if I want to go back to the original equation, what do I have to do? How do I turn a derivative back into the original function? Antiderivative. And what would that antiderivative contain? Every antiderivative is in terms of what at the very end? A C value, right? So the differential equation, a general solution involves C. A general solution to a differential equation involves some constant C. We're also given this statement here. F of 4 equals 2. This is called an initial condition. An initial condition for the original function. I want to write the equation that has our given f prime of x as its derivative and also passes through this point. I can use this extra coordinate, I can use this extra initial condition to find the right C value so that my solution has the given derivative and also passes through this point. So let's do that. Let's find the antiderivative of f prime of x dx. If I take the antiderivative of the derivative, what does that produce? The original function. So once again, if I take the antiderivative of the derivative, I get back to the original equation. So the antiderivative of 1/2 x minus 1 dx. What would the antiderivative of 1/2 x be? Term by term. What term has a derivative of -1?
Negative x.
Don't forget the C. All right. So here's our original function. Let's call that f of x. Any function of this form, any function that is of this form would have f prime of x as its derivative. We agree with that. So we've kind of satisfied part 1. My solution will be of this form. But aren't there an infinite number of solutions because C could really be anything? This is the general solution. Because generally speaking, C could be anything and it still has the right derivative. Now, more about that initial condition. How could I use that initial condition to solve for C?
So 4 for x.
And set it equal to? Set the whole thing equal to what value then? When I plug in 4, the whole thing should be equal to 2. The value of the function for what x is 4 has to be 2. What C value makes that so? What C value correctly evaluates the function so that when I plug in 4, I get out 2? So let's use this to solve for C. All right, so let's see here. 1/4 of 4 squared. Minus 4 plus C equals 2. Four squared would be 16. 1/4 of 16 is 4. Minus 4 plus C equals 2. 4 minus 4 cancels itself out. C is 2. Let's use that and write the particular solution. What singular function has 1/2 x minus 1 as its derivative and has a value of 2 for when x is 4?
1/4 squared minus x plus 2.
Using the appropriate c value, given our initial condition, I can find the singular function that has the given derivative and passes through a given point. This is, once again, what's called not the general solution, but the particular solution to a differential equation. Because it is the particular function that satisfies the initial condition. For when x is 4, the function is equal to 2. All right, so up on the television screen, I've got kind of that same statement for what we just did, graphed visually for you. I've got the general solution, f of x equal to 1/4 x squared minus x plus some constant, call it c1 in this case. I've also got the coordinate 4, 2 labeled. When x is 4, my function has a value of 2. What value of c is necessary so that this function passes through the given point? We solve for it, and it has to be 2. If I set my slider to 2, now it passes through that point. There are an infinite number of functions that have f prime of x equal to 1/2 x minus 1 as the derivative, but only one of them satisfies the initial condition. Only one of them has a value of 2 for when x is 4. Okay. Why don't you guys try the one just to the right of that? dy dx equal to 1/x squared, given the derivative, and a point on the original function, 1, 0. To solve the differential equation means to produce the particular solution that has dy dx as the derivative, satisfies the initial condition of 1, 0. Hunter, can you see my board okay? We're just kind of working on this next example here to the right. What? Some people try this before.
Yeah,
minus hand plus c
Solve for C. Solve for C. How can I rewrite 1/x squared so that it's easier to anti-differentiate? Take antiderivative of x to the -2. What will my new exponent be if I add 1 to -2? What's 1 more than -2? -1. If we get the plus c, because we're still working with the general solution first, I haven't solved for c yet. Let's see here. If I take the derivative of this, does it match the function up above? What do I need to have out in front? Make it -1. The derivative of this would just be -1 x to the -2. I want +1 x to the -2, so I need another negative out in front to make sure the signs match up correctly. So our general solution, let's call it y equals, instead of f, we're using the explicit version. Y equals -1/x plus c. How do I solve for c? Okay, well, which one's the x coordinate, which one's the y coordinate? When I plug in 1 for x, the function's equal to 0. Substitute 1 in for x, substitute 0 in for y, solve for c. Any function of this form has 1 over x squared as the derivative. I want to find the singular solution, the particular solution that also satisfies the other initial condition. So when x is 1, y is 0. 0 equals negative 1 over 1 plus c. Means 0 equals negative 1 plus c. C has to be 1. So y equals negative 1 over x plus 1 should be the particular solution and solution to our differential equation. And if I put this back up on the screen, I had this next example graph on Desmos above. We want to find the right c value that puts this function through the coordinate 1, 0. And we solved for c equals to positive 1. Let's make sure the point turns on. There we go. When I have the coordinate 1, 0 labeled with the c value of 1, my particular solution also passes through that coordinate. Thoughts there, guys? Any big difficulties there? Basically, it's just taking the antiderivative and adding on one more step, right? Solve for c. All right, here's a good physics application on the other board. Slide it around. A good physics application when it comes to vertical motion. A ball is thrown upward with an average velocity of 64 feet per second from a height of 80 feet. When does it hit the ground? Now, I'm sure some of you remember the position function for particle motion. Given the initial velocity and initial height, you can write a function to model the height of the object over time. But we can also use antiderivatives to find the position function for this object. Let's start with the acceleration due to gravity. Maybe you know it for meters, maybe you know it for feet. Since we're using units of feet, what is the acceleration due to gravity given in feet?
32 feet per second.
Yeah, but since gravity is falling, it'd be negative, right? Gravity's going to pull the object back down. So our acceleration function, or s double prime of t, the acceleration function is the double derivative of the position function. It's the rate of change in the rate of change, so it's the derivative twice. That'd be negative 30. Acceleration in terms of time is the double derivative of the position function. So we're going to call that negative 32 feet per second here on planet Earth. Negative 32 feet per second here on planet Earth. We're trying to get back to the position function. So how do I take s double prime and turn it back into the original position function s of t? How many derivatives do I have to undo? 2. So I have to anti-differentiate 2 times. If I take the antiderivative of the acceleration function, what does that produce? Velocity. S of t, v of t, a of t. From top to bottom, the rates of change in each other. So this would be the derivative. From bottom to top, you just reverse the process. It's the antiderivative. So let's take the antiderivative of negative 32 dt. What term in terms of t has a derivative of 32, negative 32,
Negative 32t.
plus
C.
c. So that would be our velocity function, or s prime of t. We undid one derivative, so now we have the first derivative instead of the double derivative. Is this a particular solution or a general solution? How can I make it the particular solution? How can I get rid of the c value? Do I have any other information about the height or velocity of this ball?
Velocity is 64%.
What time would that be at? When time is what, the velocity is 64. So the time would be 0. When I substitute in 0, the velocity should be equal to 64. So let's solve for c using that setup. 64 equal to negative 32 times 0 plus c. When time is 0, velocity is equal to 64. Well, what's 0 times negative 32?
0.
That constant c has to be 64. So here would be our velocity function, or in other words, it's s prime of t. It's the first derivative, it's the rate of change in the height over time. Negative 32t plus 64. We're getting closer. I have the velocity function. I want to describe the position function so I can use it to see when the object hits the ground. But what I have to do, I still have the velocity function. I can't just plug in 80 yet. I have to find the velocity function first. I have to undo one more derivative. How do I do that? Take the antiderivative. Let's find the antiderivative of negative 32t plus 64 in terms of t. dt in terms of t. What is the antiderivative of the term negative 32t? I know it's got to be t squared.
16.
Negative 16. So if I pull down the 2 and multiply it with the negative 16, I get back to negative 32. (64) should be 64t plus what else? Another constant, right? There is s of t now. I took the antiderivative of velocity function to produce the original position function. Now I have a function that describes the height of the object at any time that I want. Is this the particular solution or the general solution? Because c could be anything. How can I solve for c again? What else do I know? The initial height of the object. When time is what though, Shay? The height is 80 when time is 0. So let's substitute in 0 for t and set the height equal to 80. Solve for our constant c and get the particular solution from this general solution. So 80 equals negative 16 times 0 squared, that's nothing, plus 64 times 0, also nothing, plus c. What does c have to be? 80, it's the initial height. So our position function is c equals 80. Our position function has to be negative 16t squared plus 64t plus 80. When you're writing the position function, in general, this term is always a negative 16, in terms of feet at least. The coefficient on the quadratic portion is negative 16. The coefficient on the linear portion is your initial velocity, and the constant is always your initial height. We just did the same thing by anti-differentiation. Now the question says, when does the ball hit the ground? How could I use this position function I've now produced using anti-differentiation? Solve for that time value. At what time does the ball hit the ground? Set what to 0? Right, set this whole thing to 0. Solve for the correct time that makes the height equal to. How can we solve for t? We've got a few different options available for us. To solve for t, what options might be worth exploring? Take a look. Factor out of t? 8? I think I could factor out a little bit more than that. I could factor out a 16. I can also use quadratic formula. If you just want to use quadratic formula right away and plug negative 16, 64, and 80 into quadratic formula, that would be fine too. I don't know, I like to factor first, so let's go factor. I'm actually going to divide everything and factor out a negative 16. I like to factor when the quadratic term is positive, so let's just factor out a negative 16. Negative 16 times what makes positive 64? Minus 4. Negative 16 times what makes 80? 80 divided by negative 16 is a negative 5. Your algebra 2 skills here, your algebra 1, algebra 2 skills. How do I factor this? What multiplies to make negative 5? It adds up to be negative 4. So my two factors are t minus 5 and t plus 1. Set each factor to 0. All these multiply to 0, so either one of them could have been 0 to make that true. So t minus 5 equals 0, t plus 1 equals 0. That means that t equals 5 seconds, or t equals negative 1 second. Does that make any sense? Have a time value of negative 1 seconds? No. See you later. The ball hit the ground 5 seconds after launch.
So we don't have to worry about the negative 6.
Can negative 16 ever equal 0? The only solutions come from the factors that in terms of t. Good question, though. You factor out negative 16, and then it's really no longer a part of anything getting towards a solution. I just need to know that the ball hits the ground after 5 seconds from launch. All right. Let's do this then.